Midterm material. Yes, that was yesterday. Anything we covered up until yesterday is kind of the cutoff. And yeah, you can reference whatever. Lectures, books. Just don't use AI, please. I can tell if you're using AI. I have a couple students I'm suspicious of that I'm going to look at what happens on this next exam. So if you're doing it, please don't do it again. Otherwise, I have to, like, do things. But yeah, y'all be fine. Will the previous midterm pop up on the second midterm or only the final? Only the final. Yeah. Well, I mean, everything in physics is technically cumulative, but I will say, yeah, going from like waves and fluids to E&M, that doesn't really transfer as much. If this was mechanics, then I would say 100% what you did on midterm 1 is expected for midterm 2, because usually midterm 1 in mechanics, you learn like kinematic equations, you learn, I don't know, forces and stuff. And then if the next midterm is doing centripetal acceleration and forces, you still need to know your kinematics equations. But I will agree that in 1B, this midterm, because it's mainly just electrostatics, that doesn't have as much carryover from waves or fluids. Yes, you can email Albert as many questions as you want. During business hours? Yeah. I mean, during like regular times, I guess. But yeah, you can email Albert as much as you want. Yeah. I mean, within reason. Don't send him like 30 emails or something. Yes, I need to finish the draft and get it to him so he can go over it tonight or tomorrow. Poor Albert. Yeah. I do try to make Albert's life a little bit easier, though. I handled all the regrade requests. I didn't make him do any of that. I was like, I'll do it. It's okay. I know some like more like tenured professors literally don't grade any of the exam. They just give it to the TAs. I'm like, all right, you're in charge of grading this. And I don't know. That to me is like a little mean. Also, I kind of like to see how you guys are doing. So like, I mean, nobody actually enjoys grading, but I do get some satisfaction in seeing that, like, oh, this is where people are getting things right, this is where people are getting things wrong, and it helps me calibrate what I'm teaching and how I need to teach you guys. But yeah, so today's lecture we're going to go over circuits. We're starting a new chapter. It's the last chapter over the rest of the course. It's a pretty long chapter, though. Oh, there's a little bit of lag. Oh no. Says we're okay for now. Hopefully it evens itself out. What's up, Phantom? Okay. What's up, Mistral? We'll get things started here in a second. Let me pull up the chapter. Right, we're doing direct current circuits. Okay. Nice. Let's start things off. Some quick announcements. Right, we have a test on Friday. Same format, same everything as you did for the first exam. Just different topics. We'll do the same idea of, the exam will be released at 12:30. You have up until midnight to complete it. Make sure your answers are put into Kudu. And then also, please upload your work onto Gradescope. And we'll give you like a PDF thing. If you want to fill that out, it just makes it easier for us to go through. I know some people like do their own paper and then just write wherever, but how Gradescope works is it organizes the questions by like the pages that are submitted. So if you use the PDF we give you, that's great. Gradescope will automatically know what to do with that. If you want to use your own paper, you can, but I ask like try to keep the formatting the same. So I think how it works is like there's 2 questions per page maybe or something. So don't do like 1, 2, 3, 4 all on one page if on the PDF it's like 1, 2, and then the next page is 3 and 4. It just makes it easier, and it's good practice for the final because the final is going to be a little bit more intense with partial credit. If we notice an error in our work after we submit our work to Gradescope, would we resubmit the whole thing? I mean, yes. As long as you... I don't know the specifics of how Gradescope works, but I imagine you can edit your submission up until the deadline. So if you notice an error before the deadline, I think you can just take your submission down and just re-upload it. And then maybe resubmit the whole thing. Yeah. I mean, double check your work. Just make sure things are okay. Again, you have until midnight to upload it. So you got a little bit of time. Again, the final will have a shorter window. So, we use these midterms as good practice for you to get comfortable with how do I submit things so that on when final exam comes out, I don't have like 30 emails saying like, I missed the deadline to upload my thing. And I'm like, okay, but we've had a lot of practice on the midterms at this point, I hope. Yeah. Also, set reviews are still out and open. You guys are doing pretty good, actually. If we look at, oh, it's getting the wrong page now. Damn it. One sec. Here we go. Wait, one sec. Let me move this all over. That's annoying. OBS, you silly goose. Pulling the wrong page. Okay. There we go. Now I want to see it. There we go. Okay, cool. So, yeah. You guys are at 32%. Pretty good. Remember, 80%. We get 80% of the class to fill this out. Everyone gets bonus points on their final grade. So, if you haven't done it yet, try to do it as soon as you can. You have up until the 29th, which I think that's like next Tuesday, but it's like Tuesday morning. It's at like 8 a.m. So, please try to do it this week, or at least over the weekend, because, yeah, otherwise you're going to forget, and you'll miss the deadline. But, yeah, make sure to do it. Yeah, it's cool. It helps us out. The university understands how professors are doing. I like the feedback because I can figure out what you guys like, what you guys didn't like. It's all anonymous, too, so you can say whatever you want. I got some pretty interesting comments last quarter. Where is this again? Good, okay. I believe, well, here, let me pull, there's a QR code for it, actually. One second, let me pull it up. I threw it on Discord at some point. Dun, 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 dun. Let me get it for you guys real quick. Okay, so this is the QR code. If you want to scan that with your phone or something, like, if you're watching on your phone, I guess it's kind of hard, but you can take a screenshot of it maybe. And then here's the link. I'll post the link for you guys if you want it. I think this link works. So go there on that link. That should allow you to fill out the student experience of teaching survey. Yeah. So help yourself out, help your fellow classmates out, write a review, like and subscribe, all that fun stuff. Okay. Let's see. I'm going to move Kudu over here. Okay. So, welcome to week 5, second to last week. Lecture was this 1, 2, lecture 3. Okay, cool. Okay, so today we're gonna talk about circuits, like DC circuits. The DC here refers to what's called like direct current, which means that current like flows in only one direction. So we say like, flows in one direction. I believe in 1C you'll deal with what are called AC circuits. So the other one is AC circuits. And this stands for alternating current. And what happens there, again, you don't need to know it for this class, but AC circuits, the direction of current like flips at a rate. So it goes flip, 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 flip. And that's actually how most of the electricity in your house and everything, that's all like an AC signal. There's reasons for this, why we like things to AC versus DC. It has to do with like transmission. One's like, I think AC is safer for you than DC. But for the time being, we're just going to concern ourselves with DC circuits. Okay, so DC circuits arise because you have what's called an EMF, or the word, what this stands for is electromotive force. So way back in, let's see, what's the historical context of this? When did they come up with EMF? Alessandro Volta in the 1800s, he believed that the ability to like push a current, right, to push electrons around in a wire, was similar to what physics was doing with mechanics, right, and that it was just another sort of force. Turns out, right, EMF, electromotive force, is not technically a force, but how we usually refer to this is in terms of volts, and we call this like the voltage of a component is the EMF. A lot of the standard EMF source or voltage source that we're going to deal with, and then we've kind of already dealt with and when we're dealing with capacitors, is a battery. So battery is an EMF source. What's up, Taco? Okay. So, yeah, they say other sources of voltage. There's some cool little pictures here. Let's see, what do they got? Oh, okay. So some other sources they talk about is, for instance, like wind farms. Wind can create voltage, EMF source. The way it does it is it basically like runs a motor in reverse. So usually you need like voltage and current to spin a motor, but if you get something else to spin the motor, then the motor generates the same voltage and current that would have been required to spin it. So that's how like turbines work, or in this case wind turbines. These are water turbines, and so it's kind of the same concept. You have some sort of fluid moving past a propeller that spins a motor, and the motor generates the electricity that would have been needed to spin it in the first place. And then you have solar farms that's using what are called voltaic cells in order to create electricity, which I believe is taking the photons from the sun and having it like bounce off of like different chemical things that like release electrons, and that creates a current. And then we have batteries. Batteries is the standard one we use. Right. So when we talk about an EMF source, again, we kind of have like the idea of what is the conventional direction of current, right? So if you have a battery, for instance, right, this is a battery. The battery has terminals. Terminals is where you connect the EMF source or the battery to different components. So this, for instance, this is like a terminal. This is like the positive terminal, and this is the negative terminal. And between these terminals, you have an electric field, actually, that is running, again, from positive to negative. And in doing so, this creates a force on the electrons, okay? So what that does is that's going to pull, or let's see here. Is this correct? Their diagram might be wrong here. Wait, what? Electric field is opposite. Oh, okay. Okay. They're drawing this in a weird position, but if this is positive, what it's doing is it's pulling electrons this way, and then in this direction, it's repelling them away. I don't know why they're drawing this in the middle, because this electron does not move from here to here. Electrons are towards, right? And we know from F equals QE, right? That if something has a negative Q and the electric field is positive, then the force on it is negative. So here, yeah, the force due to an electric field on an electron is always opposite to how it's moving, right? So you end up getting a current that flows in this direction while the electrons end up moving in this direction. Yeah. Interesting. Okay. Okay. You don't really know that much about, like, again, EMF and all this stuff. It's kind of like the nitty gritty of things. Really, what we deal with is voltage, and where that comes from is the potential within a battery, and that is designed using chemistry or electrochemistry. If you guys remember voltaic cells from maybe like your AP Chem class or something, you can use different chemicals to create like an anode and a cathode. Within, you have like, again, like some sort of solution. Then you have like a cathode and anode, and like one's like an electron acceptor, one's an electron donor, and that creates like a voltage difference between the two. And that voltage is the EMF. So here they say it shows a single cell, one of 6 of this battery. The cathode is connected to a lead oxide plate, where the anode is connected to the lead plate, and they're immersed in some sulfuric acid, right? That's the electrolyte, that's the charge carrier. And that's what creates a potential difference between the anode and the cathode. Yeah. Cool. Yeah. And the way I remember it is, right, cathode is positive, and then the anode is going to be negative. Okay. Now, within batteries, there actually is a small amount of internal resistance within a battery. So when we look at a battery as such, remember that this is our diagram, right, for how we write like a voltage source. It turns out there is like some sort of internal resistance between the terminals. So it's not technically a pure voltage source. And that resistor is in series. And we'll talk about like what resistors do in series in terms of current and voltage drops. It's usually pretty like negligible. We don't really consider internal resistance. It's not we're not really going to deal with it in this class. I'm not going to have you guys measure like internal resistance of a battery. You can just always assume the battery delivers the voltage it says it does. But in the real world, there is a small amount of internal resistance in the battery. And yeah, I guess you could derive it if you wanted to. You wanted to figure it out. Okay. Battery testers. Yeah, sure. Okay, let's get to the actual fun stuff, which is resistors in a circuit. Okay. So, for a standard circuit that looks like this, okay? This is going to be a resistor. Okay, and this is our battery, which again has a positive terminal and a negative terminal. And then let's say this has some resistance, I don't know, like let's say like R0. Let's say this has some voltage V0. Current is then going to flow from the positive end of this battery to the negative end of the battery. Right? That's going to be current. And as it does so, right, we can calculate where this drop in voltage has to happen, right? So here, let's say you have like positive 12 volts, and here you have 0 volts. In reality, this is the same thing as positive 6 and minus 6. When we talk about voltage, it's usually referenced to the, the delta between the positive terminal and the negative terminal. I think an easier way to talk about this is always just say that ground is at 0 and that the positive terminal is whatever it is referenced to the negative terminal. So positive 12 and 0. But in order for the voltage here to have dropped from 12 to 0, it must have gone somewhere, right? So that's where we can say like, oh, well, there was this component in the way that had a resistance. And what we learned from Ohm's law earlier, right, was that V, or really you should say like delta V, so it's like the change in potential across of something, is equal to the current times the resistance. What's up, Aleph? So looking at this resistor, on this side, you have positive 12 volts. On this side, you must have 0 volts. So the delta V across that resistor has to be 12. We don't know what the current is. We can solve for that. And then the resistance, well, oh, that's R naught. Let's say, for instance, R naught was just equal to 6 ohms. Okay. You can now determine the current running through this circuit. And so this becomes I times 6, which then gets you 12 over 6 is equal to I. So I is equal to 2. And then remember the unit for current is amps. So 2 amps. This is the most basic circuit that we talk about. And we're going to get into more complicated circuits and try to determine the voltage and the current on everything. But usually what you want to end up doing, similar to what we did with the capacitors, is you want to group everything eventually into a single big resistor and then start breaking it back down into more complicated parts. So before we talk about like more complicated systems of resistors, we have to talk about like series and parallel. You've already done a little bit of this with capacitors, right? So this, for instance, are resistors that are in series. Notice it's like head to tail, right? All connected, like human centipede or something. Whereas when resistors are connected in parallel, all of the heads are connected to a single point, and then all the tails are connected to a single point. If this was connected to a battery, for instance, let's say this was positive, and then this was minus, right? This would be plus, minus, plus, minus, plus, minus, plus, minus. Whereas here, if this was, again, a plus and a minus, this would be plus, 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 minus, 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 minus. So if all the positive ends are connected to the same thing, things are in parallel. If they alternate, then they're in series. Yes, when I think of heads and tails, I also think of the Human Centipede. Great movie, right? Don't watch it. Okay. All right. So here's kind of like I wanted to say the confusing thing in your head is that resistors are opposite to capacitors. So we learned earlier, right, how capacitors add in series and how capacitors add in parallel to get like total capacitance. It turns out it's the opposite math for doing it for resistors. So for resistors connected in series, okay, R total is equal to R1 plus R2 plus R blah, 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 blah. Okay. For resistors connected in parallel, R total is equal to 1 over R1 plus 1 over R2 plus 1 over R dot, 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 all to the -1. This is flipped because for capacitors. Capacitors, like this type of math works for series, and this type of math works for parallel. So don't let that confuse you too much. And then the other key thing here is that for resistors connected in series, they have the same current, but they distribute voltage. And for resistors in parallel, they have the same voltage, but they distribute current. And what we'll say here is that higher R equals will get you lower I. Here, higher R gets you higher V. So we're treating it just like capacitors. In terms of like the series and parallel, like how to identify things in series, things in parallel, correct. That is the same as capacitors. In terms of finding out the equivalent resistance, it's flipped from capacitors. So remember that for capacitors in series, you had that C tote was equal to 1 over C1 plus 1 over C2 plus blah, blah, blah to the -1. And that for capacitors in parallel, you had C tote was equal to C1 plus C2, yeah. So the math like switches. Yeah. All good. No, you're good, Sid. What is the same though, right? So for capacitors in parallel, they had the same voltage, but different charge, right? Different Q. Whereas for capacitors in series, they had the same Q, which is similar to current, right? Because current is just the rate of charge that's flowing, but they had different voltages. Why does the math flip? That's a good question, actually. So with capacitors, right, we saw how like plates, right, in parallel could be thought as like one solid plate. So, right, when we had capacitors, it looked like this. We could think about like, oh, like, well, this is all just like one solid plate altogether. And it has to do with like how capacitance is measured, right? Because capacitance is measured as, Q over V, right? Whereas resistance is measured as V over I. Do you see how this is flipped? So here for capacitance, voltage is on the denominator. Here for resistance, voltage is in the numerator. And that flips like how you add things. I think this is called like harmonic averaging is what it is. Where this is just like a straight average, or, you know, if you divide it by the number of things that are there. But for resistors, why this makes sense. So something we should notice here, right, is that the total resistance goes up as you add more resistors, right? So let's say, for instance, here, let's say R1 equals R2 equals R3, and let's just say it equals what number do I want to use? I'll use 9 or 3. Let's say it's all equal to 3 ohms, okay? So if I were to put these in series, right? Let's say we had like R1, R2, R3, okay? Then R tote would be equal to R1 plus R2 plus R3, which would be equal to 9. So do you see how like putting more resistors in series gets you a bigger resistance than a single resistor? However, let's try to do it here in parallel, okay? Now you have, okay, well, my R tote is equal to 1 over 3 plus 1 over 3 plus 1 over 3 to the negative 1. Well, 1/3 plus 1/3 plus 1/3 is just 1. So you get R tote is equal to 1 to the negative 1, which is just equal to 1. So notice here, right? The equivalent resistance is less than a single resistor, right? A single resistor here had 3 ohms of resistance. But if I put them in parallel, now my equivalent resistance is less. The reason for this is that charge is always trying to move from a positive to a negative side, right? It's always trying to do this. When it has to go in series, it's like hitting roadblocks. It has to go like, it has to hit this, has to hit this one, has to hit this one, has to hit this one, okay? And that makes it more difficult, right, than just going through one. When things are in parallel, now, instead of the current going through all of them, it gets to split how it goes through. So now the current has to go through less resistance in total because the whole thing is not going through one resistor. You're dividing it. You're like splitting up you're splitting up the flow of the electrons through 4 different lanes. You can think about it in terms of traffic. Imagine you had traffic, right? And then these were like stoplights. If you got to go through like 4 stoplights in a row, that sucks, right? It's going to take a while for you to get through that road. But let's say, for instance, instead of there being 4 stoplights in a row, there's 4 different lanes with stoplights. Well, now traffic can divide itself amongst the 4 different lanes, and so you can probably get all the cars through faster than just going through one lane, right? This versus going through a single lane, right? This is still pretty brutal. It's not as brutal as going through 4, but if you split the traffic amongst 4 different resistors that you can go through, now it's even faster. So, yeah, it is kind of the flipping part. Yeah, there's another like flip to it, right? So, equivalent resistance is higher for series. It's lower for parallel. And it has to do with you're creating more paths for the current with parallel. So, it doesn't have to go through as much resistance. Does that make sense so far? Okay. We do have some clicker questions on this. Trying to wrap my head around it. It's okay. If you're seeing it for the first time, it can be kind of difficult. It'll eventually make sense. Again, I like to think about current as, traffic, like cars. And resistors are stoplights. Howdy, y'all, actual location. Well, all right then. Lol, I'm in Epic. What's up, Yanni? Okay. Let's see. We got some clicker questions here. So, first one here was 2 identical resistors of resistance R ohms are connected in series. The equivalent resistance of these 2 resistors is... So, let's see. And then let me get you some answers. Okay. two identical resistors of resistance R, the equivalent resistance of them is. Right, so we said when things were in series, right? Which was up here, right? R total is equal to the sum of the resistors. This is like the equivalent resistance. So in this case, equivalent resistance is more than each individual R, right? Because here we would say like, oh, well, R total is equal to R plus R, which is equal to 2R. So that's going to be greater than R ohms. So that's going to be answer choice A. Nice. Okay, then another follow-up question about resistors in series. So what we ask is, which of the following must be true about resistors connected in series? The equivalent resistance must be less than that of any single resistor. Well, that's false, right? Equivalent resistance is less if they're in parallel. The power dissipated in each one must be the same. So let's remember the equation for power. P is equal to IV, right? So I don't know if that's necessarily the same, right? Because although things in series will have the same current, they're going to have different voltages. The electric potential across each resistor must be the same. So that's voltage. So voltage is the same when things are in parallel. Remember, parallel, same voltage. Gay. Substance station. Did we figure out who that actor is? Chung Young or something? What's his name? So in this case, the answer is going to be D. The current flowing through each resistor must be the same. So remember, for things in series, they have the same current, different voltages. Voltages distribute. So this answer choice is going to be D. But I like the guess, Sib. Good guess. Okay. So then let's continue on with a little bit about resistors in parallel. Oh, it's not Bolo Chung? Who is it? He's Korean, but he's also like a doctor. He's like I think he's a Korean actor that is also he's a medical doctor. He gave up a pretty lucrative profession to be an actor. Oh, Ken Jeong, that's it, right? Yeah, Ken Jeong. Was he on like Saturday Night Live or something? I feel like he was. Okay, resistors in parallel. Oh, sorry. So let's remember, things in parallel have the same voltage across them. So yeah, that is going to be answer choice A. Well, right away, we get that. Cool. Power dissipated being the same. Nope. Power is I times V. And for things in parallel, they have the same voltage but different currents. So the power can be different. Same current must flow. Nope. That is things in series. Equivalent resistance must be greater than. That's also for series. And then the equivalent resistance is equal to the sum. This is also for series. These are both for like series circuits. Okay. So that should be answer choice A. Nice. Oh wait, did it check? Yes, good. We're good. Okay, we're going to get eventually into the light bulbs and stuff. Let's talk about like breaking down circuits, more complex circuits into easier circuits. Let me find a good example we have here. Combinations. Yeah, ooh, here we go. Love it too, Yanni, dude. You're good. Okay, let's say, for instance, And this is, again, very similar to what we did with capacitors. But let's say we have a circuit where this is V0, which is equal to 12 volts. Let's say it hits a resistor here. Let's say R1 is equal to 1 ohm. And then it's going to split into this. This is going to be R2, which is going to be 6 ohms. This is going to be R3, which is 13 ohms. And then have it come across, come back down. And what they can ask you here, I mean, this is a very typical question. They could say, okay, what is V1? What is V2? What is V3? What is I1? What is I2? What is I3? Okay. So, the major strat we want to use with this is we want to try to convert this complicated circuit down to the very basic circuit, which is just battery and resistor. Because once I have just a single battery with a single resistor, I can use V equals IR to figure out anything about this. And then we can break it down to get more information. So the first thing I'm going to do is I'm going to try to turn this system into a basic system of just a single resistor. And what that means is I want to try to convert all of this into one resistor. That's what I'd like to do. Okay. Now, what I should know, this is where, like, you may not see it immediately, but after enough practice, you start getting a hang of it. What I want to do is I want to combine resistors. And Sib is correct. Yes, the first thing you want to combine is you want to combine R2 and R3 because these are in parallel. Okay? So I'm going to come up with some new resistor. I'm going to call it R23. And remember, for resistors in parallel, that's going to be 1 over R2 plus 1 over R3, all to the negative 1. So that's going to equal 1 over 6 plus 1 over 13 to the negative 1, which, ooh, I don't think that's a nice number. Man, they should give you nice numbers for these. But okay. Gotta be mean. Okay. 1 over 6 plus 1 over 13. We're going to do that to the negative 1. And that gets us 4.1 ohms. Okay, so this is equal to 4.1 ohms. All right. So now I have a new circuit, which is just going to be, right? So again, this is 12 volts. This is R1, which is equal to 1 ohm. And now we have R23 here, which is equal to 4.1 ohms. Okay. So the next thing that we want to do is we want to combine these, which are in series with each other, right? Because it's like head to tail, head to tail. So this is in series. And so we're going to come up with some new resistor, R123, which is going to be equal to R1 plus R23, which that's equal to 1 plus 4.1. This is going to equal to 5.1 ohms. Cool. So now I have a new circuit. And this is like the basic circuit, right? Of a single voltage source and a single resistor. Okay. So now this is 12 volts. This is 5.1 ohms. And we can calculate now the current for this situation, okay? So we can say, okay, well, what is this current? What is I123, right? Because this is R123. Well, using Ohm's law, V equals IR, Now you say, okay, well, 12 is equal to I times 5.1. Divide by it, and you get that I123 is equal to 2.35 amps. Cool. All right. So we got the first thing was I is equal to 2.35 amps. Now what we do is we start going backwards. Right? So now I'm going to take this and expand it back out. So let me like copy this. So we expand. Okay. And what we know about things that are in series is that they have the same current. And that includes the current of them like together. So in this case, since this is in series with this, these two things will have the same current, which is the same current as what they had as a super resistor. So here we can say, okay, cool. I1 is also equal to 2.35 amps. And I23 is equal to 2.35 amps. And now from that, from again, V equals IR, I can then solve for V1, the voltage across the R1 thing. That's just going to be equal to the current, so 2.35 times 1, so that equals 2.35 volts. And then the voltage across 2, 3, which is still the combination of 2 and 3, is going to be equal to the 2.35 times 4.1. So multiply that by 4.1. And you get 9.64. Now here's a cool thing. Notice that these two things have the same current, but look at their voltages. These two numbers add up to basically 12 volts. So it's technically 11.99, but yeah. So even though these two things have the same current and they have different voltages, their voltages add up to what the total voltage was. So we can now like start filling some stuff out here, right? Okay, so now I know that V1 is equal to 2.35. I know I1 is also equal to 2.35. So this is amps. This is volts. So let's go to work on 2 and 3. Okay, so going to work on 2 and 3. We're going to take this. So now we're going to expand this one out, all right? And what we know, right, is that V23, so the voltage on that whole thing, was equal to 9.64. But for components that are in parallel, they have the same voltage, and also the same voltage as the super resistor. So this means that V2 is also equal to 9.64 volts, and V3 is also equal to 9.64 volts. Okay, so we can actually fill some stuff in right here, right? Oh, we're good, right? So 9.64 volts, 9.64 volts. So now all we got left to do is determine I2 and I3. And again, from V equals IR, we know V over R is equal to I. So then I2 is equal to 9.64 over R2, which is 6. And then I3 is equal to 9.64 over 13. Now let's see what we get for numbers there. So this divided by 6 is 1.6 amps. And then this number divided by 13 is going to be 0.74 amps. Okay? And notice something cool here. Do you see if I add these up, I get 2.3? 2.3 amps, right? Which we said was the total amount of current going through I23. So now these currents add up. We can say like, oh, total equals 2.3, basically 2.35 amps, which is equal to I23. Cool. So 1.6 and 0.74. And there you go. That's how you've figured out the voltage and the current for every single component in this circuit. Congratulations. Liked and subscribed. Love it, Yanni. Yes. So there you go. That's how to figure out the voltage, the current for different components. And in this case, we're combining, right, something in series with something with parallel. This will end up getting more and more complicated. For instance, we'll start dealing with stuff like this. So here we can say like, I'm not going to run through doing these because I don't know, it's just kind of boring for you guys. No, not that one. So for instance here, you want to get kind of good at just like eyeballing this, right? You can see that this is in series, right? And then this is in parallel. And then you end up having the two of them together being in series with each other. So you would end up like convert, and then put them all together in this, figure out the current and resistance, and then you end up breaking it back down into the pieces. Yeah. Okay. The other thing we got to talk about is power dissipation, right? So we got to talk about like power dissipation. Okay. So what we learned from, I think it was Tuesday's lecture, was that power is equal to I times V. Okay. So the current times the voltage of something is equal to the power. And if V equals IR, now you can substitute that in. So you can get, oh, well, this is also equal to I squared R. And it's also equal to V squared over R. Okay, so these are all equivalent ways you can measure power within a system. So looking kind of back at our other example here, right? If these were replaced with light bulbs, you could determine which light bulb would be the brightest. Okay. So let's take our circuit, for example, here. Yeah, and this is the key thing. When you're talking about with light bulbs, more power equals brighter. Okay. So if they ever ask you on some question like which light bulb's the brightest, you're calculating which one has the most power running through it. So for example, when we had this one, we can calculate the power going through each component. So for instance, let's calculate the power on this one. So we say like P1. Well, it's just V1 times I1. So that's going to be 2.35 squared. So that's 5.5 watts. Okay. P2 would be equal to 9.64 times 1.6. So that's going to be 15.4 watts. And then this is going to be 9.64 times 0.74. So that's equal to 7.1 watts. And then if we remember our total circuit, what was our total circuit again? It was here, right? It was 12 volts and 2.35 amps. So when we had like V123 was equal to 12 volts and I123 was equal to 2.35 amps. You could think of like P123, so the total power in it is 12 times 2.35, which was equal to 28.2. And these are always measured in watts. So looking at our circuit here, right, the brightest light bulb would end up being R2, would be this one right here. This one would end up being the brightest light bulb. R3 would be the second brightest, and then R1 would be the least brightest. And then if you were to calculate the power dissipated in each one of these devices and add them up, notice that the total here, so it's around 28, which is pretty close to this. Yeah, because that's what, 22.5 plus 5.5 is 27. Add another one. Yeah, it's 28 watts. Some rounding errors, but you should notice that this is the same. So the power that's dissipated through each individual component adds up to what the total power being provided by the battery is. Yeah. Kind of cool. Okay, let's see. Oh, we have a clicker question on this. Yeah, let's do a quick clicker question. Okay, let's get the answer choices for this. Okay, cool. So it says a 60-watt bulb and a 40-watt bulb are connected in series. Which one is brighter? Calculate the ratio of the power produced by the 60-watt light bulb to the power produced in the 40-watt light bulb. Ooh, okay. Dun, dun. So, power rating, I think depends actually on its, yeah, circuits, yay, right, from Vox? We're doing circuits. Yeah, okay. So let's connect these things. So here, let's say we have the 60 watt. The ratio. Got me, yeah. And then this is gonna be 40 watts. Okay. 1 second. Yanni thinks it's A. Ooh. Well, we'll see. So, okay. Yeah, because this is the power rating on something, right? And let's remember that, like, power is defined in a number of ways, right? Power can be defined as this. Oh, you don't know? Oh, okay. I mean, it kind of makes a little bit intuitive sense. You would think like 60 watts must be brighter, right? So when these two things are connected in series, right? So in series, remember that things have the same current. Okay. So what we want to try to determine real quick, these are the power ratings on it, but that's not telling us that 60 watts will be dissipated in this circuit. That's just what they're rated at. And so if something is rated at 60 watts, right? Let's see here. Then you can figure out the resistance. Because how a light bulb works, light bulb is just like a wire here that's coiled around, and it has like resistance. And as current flows through it, that I times V creates power that heats it up and then causes it to illuminate. So if P is equal to V squared over R, that tells me that R is equal to V squared over P. Okay? So for the same amount of volt, so that tells me that the resistance of each thing, the resistance of the 60-watt bulb will be less than the resistance of the 40-watt bulb. Yeah, because these power ratings are done at a constant voltage. They're saying like, okay, if I plug this light bulb into a 120 volt source, this is the amount of power it takes. And so you can figure out the resistance. So R of 60 is equal to V squared over 60. And that's going to be less than R of 40, because that's equal to V squared over 40. Yeah, this is like, so rated power. Okay. Now, when looking in series, everything has the same current, okay? That means that power is equal to I squared R, because this is the same for each thing. Thus, whatever has the bigger R equals more power. So the bigger R is actually the 40 watt. Is the 40 watt light bulb, because dividing by 40 is bigger than dividing by 60. So in this case, we would say, oh, well, the power of the 40 watt is bigger than the power of the 60 watt. And it's linear with R. Okay, so if we wanted to, so our answer is that the 40 watt is brighter. You need this so bad. Okay, good. This is actually kind of a tricky one, honestly. My gut instinct, if I saw this question, would be to say that the 60 watt is brighter. But you have to remember that whenever they say the wattage on a light bulb, that's the rated power when connected to a standard like 120 volt source. So this is not 120 volts. We don't know how many volts it is. And also these things are now connected in series. Okay. If they were independently, if they were connected in parallel, for instance, right? Now the thing, now they would have the same voltage, and so power is equal to V squared over R. Now the smaller R gets you more power. It's because they're connected in series that you get kind of this backwards effect. Okay, so this would be, so, and what do they want? They want 60 over 40. Okay, so P60 over P40 is equal to V squared over 60 times I squared over V squared over 40 times I squared. That's the same. And then so you get, this is equal to 40 over 60, which is equal to 2/3. Ooh. So, yeah, it must be this one then as well, right? Can't be the other ones. Okay. So, right, correct answer choice for this one is B. Yeah, let's see. Like, if they were connected in parallel, let's say they were I just want to show you, like, what would happen if they were connected in parallel. Let's say, like, example, let's say, what if they were connected in parallel? So if they were connected in parallel, this would be the 60 watt. This would be the 40 watt. Okay? Now these two things have the same voltage. Okay? So when computing power, I want to use something that has V in it. And I don't want to use IV because they're going to have different currents. So same voltage, different current. But I can use my other definition, which is power is equal to V squared over R. Yeah. Over R. So key thing here, when I was defining, when I was doing rated power here, let's actually just replace these with numbers. I don't want to use this V here because this is going to confuse you. I'm going to say this is 120 squared, this is 120 squared, because that's how they determine the power of a light bulb, is they connect it to a 120 volt source, and they see how much current it draws, and that determines how much resistance is there. Good. All right. Okay, so this is the rated power, and this is like, we say like when connected to 120 volts. Okay. But now, this is not connected necessarily to 120 volts. So we can say, oh, P60 is equal to whatever this V0 is. So we're going to say V0 squared over R60. And then P40 is equal to V0 squared over R40. Okay? So since P40 is greater, sorry. Since R60 is less than R40, so R60 is less than R40, dividing by a small number gets you a big number. Okay? So when I'm dividing by the smaller number, R60, this tells me that now P60 will be bigger than dividing by a bigger number, which would be P40. So that's a key thing. So in parallel, the power of the 40 watt is greater than the power of the 60 watt in terms of like the brightness. But in parallel, the 60 watt light bulb is brighter than the 40 watt light bulb. And it has to, I understand why it's confusing, is because they're using the word power in like two different, we're using watts in two different cases. The key thing here is that when we talk about the wattage of a light bulb, that's what wattage it is connected to a 120 volt source by itself. When we figure out 60 watts, that's strictly a 120 volt source connected to a 60 watt bulb, and that's it. From this, you can then determine what the resistance of this bulb is, because resistance is equal to V squared over P. And that comes from our definition of power, right? Which is that V squared over R is equal to P. Yeah. Okay. And so this is how you get, so this is rated power. And then this is going to be the actual resistance. Okay, cool. That one's kind of like a mind boggler of sorts. Yeah. Okay. I hope that makes sense. If it doesn't, again, come by office hours. I'll run through it again. I want to make sure it clicks. Some of these things are kind of like counterintuitive. But with enough practice, it'll start to really click, I guess. Yeah. Okay, cool. I'll let you guys out a little bit early because I know I went overtime a lot this week. And I don't want to get into Kirchhoff's laws yet because I think it's a lot of material to cover in one thing and it'll just confuse you more. So let's sit with this. Also, I know you're preparing for your exam, so we'll go over Kirchhoff's laws tomorrow. And then we'll also really hit like the more advanced concepts of it next week after the exam so that, you know, you're not getting too crushed with stuff. Okay, yes. You're very welcome. Enjoy, guys. Come by office hours today at 5 o'clock Pacific, 6 p.m. Mountain, 7 p.m. Central, 8 p.m. Eastern. And we'll go through it. Quick question for Amelia. Sorry, so the power for the light bulbs in series cannot be determined using V because the voltage is not the same. Exactly. Yes, and then in parallel, because voltage is the same, you can just use V squared over R. That is exactly correct. Yeah. When things are in series, they have the same current. So since I know I is the same, I want to use this definition for power, because when I divide the two, the I's will cancel. Right? This will cancel with this. Yeah, cool. Okay. Enjoy the rest of your, what is today? Wednesday. Nice. We will see you tomorrow, same time, same place. Otherwise, come by office hours. Peace.